All right, so here's what I want you to draw on all of your circles. Just draw a line that goes straight out, and there's a little theta. It doesn't really matter, just be consistent, I'd say. I'm using the same color each time. I will color code it with you. Okay, so you can keep the same color each time.
Okay.
So I'm just putting a little theta there. And if you noticed, I already put the inequalities, so I basically made a squeeze theorem right here. Do you guys see it? I just made it with pictures instead of with the function. Everyone see that? We got the squeeze theorem happening already. We're squeezing, okay? And our goal is to solve this, is to evaluate this limit. That's our goal, okay? So here's what I want you to do next. If you guys remember, this point right here on the unit circle, we always describe as x and y. You guys remember that on the unit circle?
Yes.
Right?
If we learned it.
And, yep. And then if we draw a straight line down here, then that number right there is the same as the y coordinate, right? That's like the y length of the triangle. And what does the y coordinate correspond to? Anyone remember? Sine theta, okay? So what I want you to do is draw a little arrow. You're going to write a note to yourself that the length of that side of the triangle is a length of y, and we're going to describe the length of that triangle as the length sine theta. So that is some decimal that's between 0 and 1, right? The sine theta is a ratio, and we know our ratios are always between -1 and 1, so that's some decimal right there. Are we comfortable so far? Remember, you understand it as best you can, but the conclusion at the end is the important part. So if you get confused in the middle, it's okay, because the conclusion at the end is the important bit. All right? Okay, now I'm going to go ahead and take my pencil, and I'm going to draw from this point right here to that point right there. I'm just making another triangle. You guys see how I drew it? From this point right here, this xy, to where the x-axis hits the circle. And I'm going to shade that in because I'm going to find the area of this triangle right here. Okay, do we see that triangle? It's almost like that whole wedge. It's almost that whole piece of pie right there. It's just missing just a little piece because we had to straighten that side out. We couldn't leave it curved. What's the formula for finding the area of a triangle? 1/2 times base times height. All right, so for this picture specifically, we have the 1/2, and then what is the length of the base of this triangle? It's a unit circle. It's 1. It's 1 because this is the radius of a unit circle. We all catch that? So the base is a length of 1, and then what's the height of that triangle that we just drew? Sine theta. We drew it as sine theta. Whew. Okay. Are we okay? All right. Now we're going to move on to the middle picture. In the middle picture, I'm going to go ahead and switch colors. I want to find the area of this entire sector right here. Anyone remember how we find the area of that?
It was a fraction.
It was a fraction out of 2 pi, right? 2 pi is the whole circle. And so we're going to say that the area of this is going to be whatever degree measure we have divided by the whole circle. Or I guess if we're doing pies, we're talking about radians here. So we are saying whatever radian measurement we have divided by 2 pi, because that's the whole circle. So this is telling us what portion of the circle we're using. And then what's the area of a circle? What's the formula? It's pi r squared. It's pi r squared. All right, so we're going to go ahead and write pi r squared. Okay? So that's the formula for us to find this area right here. And so we do not know what the actual radian measurement is. We're not sure. We're just calling it theta for right now. So I'm going to leave the theta right there. But I do see something. Do you guys see this pi and this pi right here? What would happen with those? They would cancel. So I'm just going to say pi over 2 times, and what is the radius of this circle? 1, because it's a unit circle. And unit circles have a radius of 1. So this is being multiplied by 1 squared. Are we still doing okay? Yes. Okay, I'm going to put my inequality symbol in there. Okay, now we're going to go over to the third picture. I'm going to go ahead and grab a different color. This time, from this point right here, I'm going to draw a line that goes straight up. I've just been switching. You can just do pencil, that's fine. And then I'm going to go ahead and extend this to go further than the circle. I'm extending it to go further. All right. Can someone tell me if we have this is the angle, then what would the name of this side be right here? What would we call that? Opposite. It would be opposite. This is the opposite side over here. And what's this side called over here? Adjacent. All right. So what we need to do, because we want to do exactly what we did in that first picture. In this first picture, we found the area of that triangle. We did 1/2 base times height, right? And we want to do the same thing in this triangle. We want to be able to say what 1/2 times base times height is. So we're going to need to have a number for the base. Does anyone know what the number for the base of this triangle is? It's 1, right? Because it's the radius again. So the adjacent side equals 1. And then the height of this triangle, since this is a right triangle and it goes straight up right there, the side of the triangle happens to also describe the height of the triangle. I don't know what it is. It's just whatever the length of the opposite side is. Okay? Is there a trig function that relates the opposite side and the adjacent side? Yes. What is it? Tan. Okay, so I'm going to write this off to the side of my paper. I'm going to say that tan theta is the same as opposite divided by adjacent, right? Do we agree with that? Tan theta is the same as opposite over adjacent, except what's the adjacent equal in this problem? It equals a 1. So is it fair for me to say that tan theta equals opposite? That's a fair statement? Okay, so over here I know that the length of this side, the height of the triangle, is actually equal to tan theta, whatever tan theta happens to be. So now, do we have enough information to write our 1/2 times base times height? Now we have enough information. Okay. So again, I'm going to go ahead and write my formula, 1/2 times base times height. And then for this problem specifically, I'm going to have 1/2. The base of my triangle is a length of 1. We already said that because it's the radius of the circle. Oops. And then the height of my triangle is what? Tan theta. So what we just did is we found this area right here. Okay, do you guys see how this is the biggest area? And this is the smallest area? And this area is squeezed in between them? Do we see that? Okay. Yeah, so we set up the squeeze theorem based on areas, and now we're going to ditch the picture and we're just going to do it based on functions now. So we use the picture to help us come up with functions that we could use the squeeze theorem on. That's kind of weird, I know, but that's the best explanation I have for you. Okay, now our picture, our sine theta is a positive value because our picture happened to be in the first quadrant. But sine theta is not always in the first quadrant. That means it's not always positive. Sometimes that value is negative. You could have a negative ratio, like negative root 3 over 2 or negative root 2 over 2, something like that. So what I'm going to do to reflect that I recognize that that's a possibility in the problem is I'm just going to put an absolute value around this. And we're going to do this proof with an absolute value so that we're saying this is going to work in the first quadrant and it's going to work in the fourth quadrant. It doesn't matter where you draw it. It's going to work every time. All right? And when we have angle measurements, we can measure them positively by going up from the x-axis, but you can also measure them going down from the x-axis. So I'm going to put an absolute value sign around this as well. We're going to address both of those things. And then the same thing for tan. This one happens to be positive because we were going up, but we want to consider what would happen if we went down as well. Okay. So at this point, I'm going to clean up this squeeze theorem just a little bit, okay? So is it fair for me to say that this is sine theta, it's the absolute value of sine theta, divided by 2?
Yeah.
That's fair? Okay. Is it fair for me to say that this is the absolute value of theta divided by 2? Yeah, because all it had is multiplied by 1 squared, so I can kind of get rid of that. Is it fair for me to call this absolute value of tan theta divided by 2? Yes. Okay. They are all divided by 2. So what could we do to maybe simplify this problem a little bit? Take those 2's out. We're just going to multiply the entire problem by 2. And that's going to get rid of those fractions. All right, and this is where things start to get a little weird, so bear with me, okay? What we're going to do is we're going to take tan and we're going to rewrite it in terms of sine and cosine. And the reason we're going to do that is because our goal at the very end of this problem is to have sine theta over theta squeezed in the middle, because that's the limit we're trying to find, and we're trying to do it with the squeeze theorem. So eventually we need this to be in the middle of our paper, okay? So, and that's not going to happen if I have a tangent over here. I need to have some way of getting a sine inside here. So bear with me, okay? So we're going to go ahead and take that tan, and what could we switch tan to? Sine over cosine. So I'm just going to rewrite that tangent as sine theta over cosine theta. Okay. What I'm going to do next is I'm going to take each of these pieces and I'm going to divide all 3 pieces by sine. Okay, and you can do that in another color if you want to, like, show your work a little bit. So I'm going to divide this by sine, and I'm going to divide this by sine, and I'm going to divide that by sine. I'm doing it because I know when I look ahead in the problem, it's going to help me out, and I don't have a better explanation than that. All right. So can somebody tell me, and these are all absolute value. Yeah, what is sine divided by sine? It equals 1. So on the very left side over here, we just got a plain old 1 now. So that's good. That's an easy limit to evaluate, right? 1, we're good with that. In the middle, I now have the absolute value of theta divided by the absolute value of sine. And technically, I think you could probably write that as just theta over sine theta and put the whole thing in an absolute value. It doesn't matter that it's top and bottom. However you want to write it is fine. And then for the last piece, what happens if I have a sine theta on top here and I'm dividing the problem by sine theta? Those are going to cancel, right? They're going to cancel just like they canceled over here. But we have to be careful about what's left over. So these canceled and made a 1. These are going to cancel, but they don't make a 1. What do they make? A 1 over cos. They leave a 1 over cos in their place. It's still there. What happened to theta is your teacher was being lazy with how she said it. Okay. All right, now this is very similar. This is very similar to what we want. It's not quite there yet. Does that make sense? Similar to what we want, not quite there yet. So what we're going to do next is we're going to consider, do you see how close we are to what we want squeezed in the middle? What's wrong with it? It's upside down. So what we're going to do is we're going to take the reciprocal of all these. That means we're going to take the fractions, we're going to flip all of them, which in an inequality means you have to switch the way that your symbol is going, because if you can think about it, you took a fraction that was smaller than 1 and you multiplied it by the opposite. So that means that our inequality symbols are going to go the opposite direction now. Do you guys see how close we are to what we wanted? We are so close. Okay. Now this is part that is kind of interesting in the proof. This is one part that I think could be confusing. So what we want to do at this point is we want to get rid of those absolute value signs. We want the problem to be cleaned up a little bit more from that. So when we solve for theta, and we're talking about sine, when we do sine inverse to solve for theta, we are only allowed to use numbers for theta that are in the first quadrant or the fourth quadrant. So that means that the only part of the picture we're looking at is the first quadrant and the fourth quadrant. If I am looking at sine in the first quadrant, is sine positive or is it negative? Positive. If I'm looking at a theta in the first quadrant, is it positive or is it negative? Positive. Okay, does that make sense? Okay. If I'm looking at sine theta in the fourth quadrant, is it positive or is it negative? Negative, because those are negative y values, right? If I'm looking at an angle and I went down to measure it, so I'm in the fourth quadrant, is that positive or negative? That's negative if you go backwards, if you measure backwards. Does that make sense? Okay. So if we think about this, if we have a negative divided by a negative, what does that tell you? That's positive. That means that this fraction, no matter what I do, is always going to be positive. Because I either have a positive value divided by a positive value, or I can have a negative value divided by a negative value. All right? And the reason it ended up being two negatives is because when you deal with inverses, you measure this as negative pi halves to positive pi halves. So we consider all these angles right in here to be negative. Do you guys remember that from inverses? Maybe?
Yeah.
That was one of the things that had to do with inverses. So at this point, we can ditch the absolute value right there. We can just say this is sine theta divided by theta. All right? What are the values for cos theta if you talk about the first quadrant or the fourth quadrant? Those are x's. They are always positive, right? It doesn't matter where they are always positive. So I can ditch the absolute value there as well because it's always positive and it doesn't matter to me much. Okay. At this point, we have our squeeze. This is our sandwich. It is completely figured out. We are completely ready. We are ready to do these limits now. So I'm going to say the limit as theta goes to 0 of 1 should be what? What's the limit as theta goes to 0 of 1? It's just 1, okay? I'm going to do the same thing over here. The limit as theta goes to 0 of cos theta, and you can plug this in your calculator if you need to. What is cos theta if you plug 0 in for theta? So you do cos, you plug in 0. You get 1. All right. So if the limit over here is 1 and the limit over here is 1, then what's the limit in the middle? Guaranteed. It equals 1. That's the proof.
Wait, how did you get cosine times theta?
I didn't say cos times theta. I said cos of theta equals 1. And I got it by taking my calculator and typing cos 0. If you type cos 0, you're going to get 1. Okay. So that means that we know that this limit equals 1, and that was the point of the proof. We're going to use that forever now. That's the point of the proof. You don't have to do all those steps ever again. That's the point of the proof. That's it. Okay. Now, it can work. The flipped version can work as well. So if we were to try to find the limit as theta goes to 0 of theta over sine theta, if we were to try to do that, that would also equal 1. Okay?
Wait, I don't get that.
That's because that's if we left it right here.
Oh, that's the same thing.
It's the same thing. So this would be, you would have theta over sine theta, and if I plug in 0 right here for cos theta, I'm still going to get 1 from that fraction. And so this is the same, it's the same proof, it's just earlier up in the proof. Okay? So both of these limits equal 1, and that's going to be a key that we're going to use later on. Okay.
3 seconds.
All right, so we're going to go ahead and look at number 3. I do not think we have enough room here to be able to write number 3 well, so I'm going to do it on a separate sheet of paper. And by separate sheet of paper, I mean a note card, because that's what I can grab easily. All right. You can do it on here and just write small. You can do it on a separate sheet of paper. You can do it on the back of those other notes if you want. All right. So we're going to walk through this problem together, and then I think that after we walk through it, you might see the purpose of why we do what we're about to do. Okay? So, am I able to plug in 0 right now? I am not. Okay. So what I'm going to do with the problem right now is I'm going to go ahead and write times 5x over 5x, and you'll see why I do that in a minute. So I've got sine 5x divided by x, and I'm multiplying by 5x over 5x. And I'm going to go ahead and rewrite this, what I just had. So now I've got sine 5x divided by 5x, and I have this extra 5x I multiplied this problem by on the top, 5x over here, and I still have that x over there on the bottom. Everyone see that?
Wait, why was it sine 5x over x?
I just switched the order. These are multiplied, so it doesn't matter what order. And I did that because I'm going to show you something. Okay, so are we cool with how the 5x got introduced into the problem? I did 5x over 5x, so I'm multiplying the problem by 1. I'm changing what it looks like. I'm not changing what it equals. Okay? All right, at this point, I'm going to conclude that this right here is 1. How can I conclude that? Because it's sine evaluated at something divided by that same something equals 1. Does that make sense? So in the proof we just did, this whole thing was theta and that whole thing was theta. And this time we're saying instead of seeing theta here and theta there, we're seeing 5x here and 5x there. You guys see that? Okay, so that equals 1. That equals 1 right there. Okay? So now I'm trying to find the limit as x goes to 0 of 5x over x. What can I do with those x's? I can cancel them out. And the limit is 5.
Oh, whoa.
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 So this is a squeeze theorem limit, but we never used the squeeze theorem, and that's because the squeeze theorem was built into here. We didn't have to do it because we already know the answer from it. So even though we are not actively doing the squeeze theorem, again, it still happened in the problem. Does that make sense? It happened in the problem at some point based on this. Yes, ma'am. These ones? So this went to right here, and this came over there. And then I moved that there. And I just did that so you guys could see it more easily. Okay. All right. If you liked that one, let's try number 4. I want to show you number 4.
Wait. I don't get it. How do you get sine 5x?
Watch number 4. Oh, it's because if remember the proof? The proof had sine theta over theta.
So you just changed theta to
I just said theta was 5x and called it good. So as long as they're the same, then you can say that whole thing is 1. Yeah. So number 1, do not do that problem again. Just say it's 1. We already proved that one. That was exactly the proof that we spent all that time doing. Okay. All right, let's look at number 4. You guys ready for number 4? All right. Now, we can't fix this problem the way it's written right now. We can't do anything with it the way it's written right now. So I'm going to go ahead and I'm going to take the sine 3x and the sine 2x. I'm going to split those. And what is going to need to be down here to make that 1 happen again? We're going to need a 3x on the bottom, right? Now, we can't just introduce a 3x to the bottom. We have to multiply the top by 3x and the bottom by 3x, right? We got to do both. So I'm going to go ahead and write I'm multiplying the top by 3x, I'm multiplying the bottom by 3x. Okay? What would make this one over here become a limit of 1? A 2x would, right? So I'm going to multiply the top by 2x, I'm going to multiply the bottom by 2x. Does that make sense? Okay.
Go.
So if you look at this, do you guys see how this part right here would be 1?
Yep.
And do you see how this part right here would be 1? So those are each 1. And then when we look at what we've got left, we have a 3x left on the top and a 2x left on the bottom. So now, if we want to evaluate the limit, what happens with those x's?
Cancel.
They cancel. And what's your limit? 3 over 2. So we've got some like manipulative tricks happening here, okay?